Swayam Prabha. Digital India. Educated India.
Welcome back. Today we will move to lecture number 24. So, in this lecture we will try to talk about machining of composites. Machining is a subtractive process. Here we would try to remove the unwanted material so that we try to maintain the required shape and dimension for the finished part. Though composites are said to be near net shape manufacturing, but still when you think of a large component, a large part wherein which it has to be made by several small parts assembly, or when you are trying to do an assembly, but that means to say a male part, female part, an assembly, a press fit, if you are trying to do, then machining comes in a big way. Machining of composites is always a challenge. Why? Because the composite material is heterogeneous in nature. It has a matrix and it has a reinforcing agent. Matrix is soft, reinforcing is hard. So, we would now try to focus on machining of composite materials. Again here I would like to cover all the spectrum, that means to say polymer matrix, metal matrix and ceramic matrix composites. Okay, in this lecture first we will have the introduction, then machining of polymer composites, then cutting tool spectrum, then effect of vibration, drilling wherein which we have delamination and taper, then we will talk about milling, water jet machining and electric discharge machining. These are some of the processes. So, when you want to classify machining process, we classify into two things. One is called as contact machining, the another one is called as non-contact machining. So, in contact machining there is always a tool which comes in contact with a workpiece. Moment there is a tool which comes in contact with a workpiece, the tool has to be harder than the workpiece. The geometry is given to the tool which will have a relative motion between the tool and the workpiece to create any feature of your choice. So, the examples of contact machining are drilling, milling, turning, boring, grinding. These are some of the examples. When you look at non-contact machining means there is no contact between the workpiece and the tool. So, here the tools which are used are electrons, ions, photons, and you can also use loose abrasives. So, examples are EDM process, electric discharge machining process, chemical machining process or electrochemical machining process, laser machining process, ion beam machining process, electron beam machining process. These are some of the processes which are available for machining of composites. You have to make a choice of choosing in this big spectrum which machining process to choose. The simple difference between contact and non-contact is there is a tool, the tool has to be harder than the workpiece, that is first difference. In non-contact it is not so. The second difference is moment there is a tool in contact with the workpiece, the material removal rate is going to be high. In the non-contact, since the electrons, ions and photons are very small, the amount of material removal rate is very low. The third one is the thermal damage to the composite is not there in the conventional processes, but whereas in the non-conventional process there is always a heat affected zone in the composites. With that definition, let us get into composite materials have very high specific properties, right. I am more focused, see in the three spectrum of composites, like we have polymer matrix, we have metal matrix and we have ceramic matrix. So, in this the polymer matrix is always playing a major role because it has a predominant presence in the environment today. So, our focus will be more towards polymer matrix machining, followed by metal and followed by ceramics. Okay. So, when we discuss about polymer, it has a good corrosion resistance, it has good fatigue resistance, you can make it anisotropic in nature, it is economical when it is a small batch quantity. However, there is a non-homogeneous, that means to say there is a polymer and there is a reinforcement. And apart from that, you have other additives like filler, etc., which they are non-homogeneous in nature. Non-homogeneous in nature, why am I re-emphasizing this? Because see, as and when a tool comes in contact with the workpiece, if it comes to a matrix are always soft, and then moment it hits against a reinforcement, which is maybe a glass fiber, carbon fiber, Kevlar fiber, they are tougher, they are stiffer than the polymer matrix. So, the amount of resistance given by the reinforcement to the tool is high, and then so the tool has to apply more energy to move further, or what happens is the reinforcement tries to obstruct, and because of the obstruction the chip flow will not happen so easily. So, that is a problem, and since it is mixture of materials, non-homogeneous polymer and reinforcement, the chips which is produced during machining will predominantly be discontinuous chip. So, this continuous chip in this where the volume fraction of reinforcement is high, so you will have powdery like structure, and since the reinforcement agent are predominantly ceramics, the small powders of ceramics, when they come in contact with the tool, they try to create a third body abrasion in the presence of very high temperature, because in contact machining there is going to be a friction factor very dominant. That is why we see when you choose a tool, we should have a tool which has high hot hardness, high toughness, and it should withstand, it should be able to withstand very high temperatures. So, that is what we say, hot hardness behavior of the tool has to be very good. So, here the friction is coming, and when the friction is coming, the temperature is going to go high. When the temperature goes high, there is going to be a change in the shape, and at very high temperature, when the tool gets softened, the reinforcing agent, when it comes to three body abrasion, then there is going to be scratches and the tool wear is going to be more dominant. Okay. And anisotropic also goes by the same justification. The reinforcement, all the three properties all lead to non-homogeneous. Because of the non-homogeneous anisotropic and reinforcement properties, the chip which is produced is always abrasive in nature. Generally, what happens in metal machining, there will be 60-70% of the temperature which is taken away by the tool. But in this case, when we talk about polymer metal matrix composite, the polymer will not take any heat. So, the entire heat has to be taken only by the tool. So, basically all the heat goes to the tool, workpiece takes zero heat, plus there is going to be lot of friction, and there is going to so all temperature raises the geometry, raises the temperature of the tool. So, tool softening becomes predominant. Then now a softened environment and a reinforcing which is trying to create lot of friction there, friction and abrasion. So, it is going to have a catastrophic failure in this polymer metal matrix composites. So, this is a challenge. So, that is why people always look for a proper choice of tool while machining polymer metal matrix composites. So, this is a classification. You have to relook into the classification, because moment you are choosing a process, you have to understand what is the reinforcing, what is the polymer, what is the temperature. So, composites are divided into two classifications. One is called as natural, another one is called as man-made. In man-made, we have phase composition and we have layered composition. Phase composition will have filled composition and will have reinforced composition. In the reinforced composition, you have reinforcement with respect to geometry, and you will have a matrix material coming into existence. When we talk about matrix, there are three types of matrix: polymer matrix, metal matrix and ceramic matrix. When you talk about reinforcement, you have a fibrous reinforcement, you have a particulate reinforcement, you have flakes. Okay, when I talk about fibrous, they are continuous, discontinuous fibers, and when I talk about phase particulates, it is dispersion strengthening or particulate strengthening. So, there are two types of mechanisms which are used for particulate type. Then when it talks about discontinuous, I talk about random and I talk about orientation. So, in discontinuous I can have random and I can also have oriented. When I talk about oriented, it will be uniaxial, biaxial, triaxial and multiaxial. This is a continuous rope, I mean to say, or a roving, and this is discontinuous. With this I try to make a uniaxial, biaxial, triaxial or multiaxial. When I say biaxial, it can have an angle ply or it can have a cross ply. So, when you look into this, now it is becoming very clear. Suppose if I use a particulate type reinforcement, these particulates are basically ceramic material. So, this ceramic material is going to make a friction between the tool and the workpiece. So, this has a higher effect. Same way when you talk about fibrous, glass, ceramic material, glass fiber, ceramic material. So, here and on top of it, okay, to reduce the temperature, why can't I use lot of coolant? Coolant, MQL you can try, that is minimum quantity lubricant, or you can do flood, you can do spray, whatever you want to do, you do. But you should have at back of your mind, polymer is hygroscopic in nature. Moment it is hygroscopic in nature, the polymer is going to attract the OH. Moment there is OH present for a certain duration of time, this will try to weaken the matrix. So, you cannot tool also by using coolant. So, these are the challenges, but whereas when you use natural fiber and when you use a reinforcement like natural fiber, discontinuous, or say for example uniaxial or biaxial, if you do jute mat, if I used, here the abrasion action is going to be slightly less, and these, when the fiber gets cut, chopped off into small chips, so powdery chips, these chips, some of these chips can also act as lubricant during the process. So, the friction and the tool wear is are to some extent suppressed when you use natural fiber reinforcement. When we look at the particulate type fiber, we have seen it in big way. So, let us look at particulate type. So, in particulate type, for example, in spheroided steel, you see matrix, which is a ferrite you have, and then you have Fe3C, which is a brittle material which is hard, is getting reinforced such that the properties are enhanced. The next one is tungsten carbide cobalt. So, we see these are the tungsten carbide particles which are present, which are hard, and we have cobalt, which is a metal which is getting infiltrated, and you make a composite. Okay. Then when you take rubber is also a rubber tire, which is also a composite. So, these are matrix which is rubber, and then these are particulates of carbon which are getting reinforced for several applications. So, you can see very clearly matrix, and you can see the reinforcing agent here. The reinforcing agent is quite high. So, the tungsten is quite high. So, nowadays this tungsten carbide cobalt, cemented carbide is a good example for a cutting tool. Nowadays, they are trying to remove this cobalt itself and do a sintering of completely with tungsten carbide. So, but you need to have very high pressure and temperature for doing this. So, these are some of the things. So, I have just put all the figures, so cross section view, so that you can understand how is the dispersion and how are we going to machine. Okay, if you look at fiber reinforcement, so here you can see aligned continuous fiber. So, you see a metal here. Okay, you see in matrix metal or Ni3Al nickel aluminide, which is in a alpha molybdenum. So, by eutectotic solidification it is made. So, here is a matrix, and here are the these are the fibers, right. These fibers are nothing but aluminide, nickel aluminide, which is brittle. So, when you look at the glass fiber reinforced composite, so these are the glass fibers which are getting cut, or the other way around, you can have ceramic glass fiber tungsten which is there in a SiC fiber. So, formed by a glassy slurry. So, you can see when you try to machine, this is what you get the fractured surface. So, if you remember in the or you will see in the next lecture, we will be discussing about repairing of composites. So, here you will how to repair the composite. So, there you will see little bit more how to handle such finished surfaces. This is an example for fiber reinforcement, and the last one is for structural. You can have laminate with varying orientations, which we have discussed in length, and the other way around is sandwich composites. Sandwich composites are lighter in weight, they give a lot of stiffness. So, you have a face sheet on the top, you have a core which is of a lighter material which gives in thickness, and between the skin and the core you might have an adhesion layer, or this too gets stitched of its own by some adhesion epoxy, whatever adhesion resin, whatever you use. So, this is called as a fabricated sandwich composites. These are structural composites which are used. So, these are the different types. So, we have seen what is particulate reinforcement, what is fiber reinforcement, and structural reinforcement. When you talk about machining of polymeric matrix composite, as I told you earlier, conventional, non-conventional. So, in this, what are all the processes which are available with us which we can do machining? So, one is cutting, orthogonal cutting. Basically, orthogonal cutting means it is for shaping and planing, shaping and planing. So, shaping is used for smaller work pieces, planing is used for, planing is an operation, we do it on a planing machine, it is called as a planer. So, this is used for a very large bed or very long lengthy work pieces, we always go for planing operation. Here we use a single point cutting tool, and it is called as orthogonal cutting. The next one is turning. For cylindrical shafts or a cylindrical workpiece where you want to maintain axis symmetry, we always go for turning operation, and then we do drilling for generating hole, and then we do milling operation for generating pockets. This is also for generating flat surface or inclined surface, you can do depending upon the relative motion between the tool and the workpiece. So, these are the operations generally done. What happened to grinding? So, grinding already it produces a very small chip and the material removal rate is very low. Grinding is predominantly an operation which is used for finishing. So, here the polymer matrix composite, both surfaces top and bottom, you can always try to in the process itself you can integrate and bring in the smoothness. Okay. So, these are the very commonly used processes which are used for machining of polymer matrix composite. When I talk about non-contact type, see what happens is polymer is a non-conducting material. So, predominantly EDM process and ECM process cannot be used because the process needs a closure of the circuit. So, this will not happen in polymer matrix composite. So, these two processes are not thought of. However, in the recent research, people have tried to give a coating on top of this polymer matrix composite and do EDM process as well as ECM process, but these processes are demonstrated, but it has not gone to the industry level. The most commonly used processes are jet machining process. So, in jet machining process what we use is, we use a jet where this jet is of a very high pressure and this pressure is passed through a nozzle and then exactly focused at the workpiece. This nozzle is moved relative to the workpiece and generates a geometry. Because of the high pressure, this is used for cutting the workpiece. So, the jet can be made out of water, the jet can be made out of abrasive. The abrasives are predominantly ceramic, and these are nothing but these are particulates. There are two types of classification. One is oxide ceramics and non-oxide ceramics. So, here what we do is, these are very small particles of from 1 micron to 10 microns you can have, and it is used. So, the abrasives are small particles. These particles are pressurized and they are mixed with a carrier gas, so that they get the pressurized air exiting the nozzle while cutting. And if you want to have an hybrid of air and water put together, so those processes are called as abrasive water jet machining process. The next process is laser beam, LBM. So, in LBM process Here the photons are used, these photons are focused by a lens on top of the workpiece. So, the laser beam process has two mechanisms, one is called as pyrolytic process and the other one is called as photolytic process. In pyrolytic process, basically the photon, when it hits the workpiece, it gets it converts it into a heat energy, it melts and evaporates. The same with photolytic, what happens, it tries to scissor or it tries to break the bond, and here it does not convert into heat, the polymer is directly converted into a gas. That means to say something like a sublimation process goes on and the bonds are broken and you try to get a cut which is made. So, this is always called as a cold cut as compared to that of this heating. So, heating leads to a something called as heat affected zone. Okay. So, next one is electron beam machining. Electron beam machining is predominantly used for very small holes to be made, very small high aspect ratios holes to be made, but here also it has a problem of closing of the circuit. So, this is a challenge. The next one is plasma assisted cutting. Plasma assisted cutting is there are two types of plasma. One is called as the plasma wherein which the workpiece is also involved in closing the circuit. The other plasma is within the nozzle itself they have closed the circuit. So, those plasmas can be used for machining polymer matrix composite. However, it has a very high heat. So, we try to avoid using plasma arc welding. So, in ultrasonic machining there is a piezo crystal. This piezo crystal is attached to a tool. So, between the piezo crystal and the tool we have a horn. The shape and the length of the horn plays a predominant role to transfer the vibration what comes out of piezo crystal to the tool. Okay. So, this tool vibrates at 21 kilohertz. 21 kilohertz it vibrates, so that the tool also vibrates at the same, but the amplitude is 10 to 20 microns, that is a maximum, between 10 to or between 1 to 20 microns. So, this is used for creating high aspect ratio holes, and since between the tool and the workpiece we pass abrasive slurry. So, a slurry is passed. So, this tries to hit the workpiece, this is a workpiece, this tries to hit the workpiece and remove the material which is there in the workpiece. So, choosing a process, the reinforcement in composite can be glass, graphite, boron, alumina and SiC. So, you have to look at the size, shape of the reinforcement and decide your process. Majority of the machining happens by brittle fracture. When you talk about machining, there are two types of fractures. Machining fracture. One is called as the ductile fracture, the other one is called as the brittle fracture. So, ductile fracture is predominantly the workpiece comes out as continuous chip. In brittle workpiece we get a powdery chip. So, when you have a powdery chip, it is very difficult for you to control the surface whatever you generate. So, in ductile fracture you can control and get the shape and the roughness whatever you want. Predominantly when you do machining, people always try to convert from brittle fracture to ductile fracture, but in composites what happens, since you have a reinforcement and that is also ceramic, you always have a brittle fracture which is coming out. So, this makes the process random in nature. So, it is very hard for you to control the surface finish on the workpieces. Then depending upon the matrix property also, for example, thermoplastic, when you try to drill a thermoplastic, there will be a lot of temperature, as I told, the workpiece has to take the temperature. So, when you drill a hole, the workpiece takes the temperature and then either the hole expands or contracts when you drill a hole. Then after a few hours, this hole either tries to shrink or contract, shrink or expand. I repeat, depending on the matrix property, for example, I take thermoplastic, there can be a shrinkage or there can be an expansion. There can be an expansion of the polymer material. So, a drilled hole, the geometry changes in due course of time. The amount of volume fraction presence also plays a predominant role in generating the chip. Then part shape, part size and the number, all these things have to be thought of while choosing a process for machining of polymer metal matrix composite. The role of the matrix, which we have already seen. So, one is to reinforce the matrix material to distribute the load and to protect the reinforcement agent, whatever it is, to give a final shape. When you talk about reinforcement, it tries to take the strength. So, this is for orthogonal machining, wherein which I have put different plies of varying orientation. So, this orientation, and you can see what happens to the fiber when you change the orientation and you cut the tool. So, this is the cutting direction. Okay. So, here orthogonal cutting, shaping and planing are typical examples. You see a sharp tool, you see a blunt tool. This tool is having a positive rake angle, this tool is having a negative rake angle. Okay, this positive rake angle, and if the orientation is 0, you can see the as and when the cutting tool moves, this is a cutting direction, when it moves you see that the layer by layer it is peeling off. You can control the depth and remove the amount of layers you want to do. When you look at this, when it is a negative rake angle, you can see the fiber does not flow on top of the surface. Here the fibers are broken, and moment it is broken, it becomes like a hard abrasive particles. When it moves on top of a cutting tool, it is going to bring in lot of friction and wear. When I just change the orientation from 0 to 45, use the same tool, you look at it, the fiber gets fractured. And here when I talk about 45 with a negative rake angle, you see that again these two phenomena are fiber cutting, fiber is cut. So, here it is fiber buckling. So, that means to say there is a fiber, you try to compress the fiber, and moment you compress it fractures and it buckles up. This is delamination, which you see here. When I try to make the orientation at 90 degrees and at minus 45 degrees, you see there is a deformation happening. Deformation means it tries to bend and it tries to shear off. And here you see there is a shearing phenomena happening. So, here you see the surface, here you see the jump in the surface which is getting generated on the finished part. So, here when I do it with minus 45 degree orientation, minus 45 degree, I get a shearing mechanism. So, you look at it, depending upon the orientation of the fiber mat, you see different mechanisms come into existence, and this is just for talking about fully stacked with 45, fully stacked with 0. But generally what happens is we have a quasi isotropic. So, we would like to have varying orientation getting stacked. So, at every ply different mechanisms get into existence, and this tries to produce lot of force fluctuation while machining. This force fluctuation tries to directly affect the hardness, affect the response of the tool. So, that is why while machining composite material, we always say please use toughened tool. So, in fact, HSS, high speed steel, gives you a better performance, but the only problem with high speed steel is it cannot withstand very high temperatures, it softens and it gets worn out very fast. So, there has to be a compromise. If you use a hard tool and a stiff tool, again while machining of composites, it is going to be a problem. And here the machining, nowadays the machining happens at 100 meters per minute. So, at that speed, force fluctuation, the tool response becomes very poor. So, if you look at CFRP and GFRP, this is the glass fiber and this is the carbon fiber. You see that when it is cut at different time scales has been given. So, when it is cut, you see the amount of damage it is getting created while machining. So, what are these damages? These damages are going to lead me to delamination and other defects. So, this is directly proportional to the life of my composite part. Okay, this is going to be directly proportional to the life of my composite part. So, I would like to do as small damage as possible, and here in carbon fiber the damage is less because carbon is having better stiffness, or it can take little bit of fluctuation in the force carbon can take as compared to that of your glass fiber. So, you can see here this is, you can see crushing happening just before the tool, right, at varying time scales. So, at varying speeds when I do, so you see that the chip flows in different directions, right. So, this you can see again I have compared with glass fiber and carbon fiber. So, here is the spectrum of tools which are available in cutting. So, here if you have to choose a proper tool for getting better performance. As I told you, this property in x axis you have toughness, bending strength and then feed. So, here if you see HSS and coated HSS gives you a wonderful performance, but the cutting speed, wear resistance and thermal resistance are extremely poor for this HSS. We would like to have higher toughness, we would like to have higher wear resistance and thermal resistance, we would like to go for higher cutting speeds. So, what we want is, we want a material here to machine composites, but unfortunately today we do not have any material, tool material which can do very good composite cutting. Though in a tool there are two things, one is tool material, we have tool material as well as tool geometry. Geometry can be generated, but the tool material is a challenge. So, we would like to have materials in this zone which is not available today. If you see tungsten carbide cobalt, it has a slightly lesser toughness, but the speeds can go high. If you keep going, you see alumina reinforced, this is a ceramic composites, alumina, a ceramic composite, alumina reinforced with TIC. You have, so this is having a very, it can go to high speeds, but the toughness goes very high. Boron nitride gives a very high wear resistance, it can help you in going to very high cutting speeds, thermal resistance, but the toughness is very low. But while machining composites, we need to have a tough tool or tough tool because of force fluctuation. What happens? You can see different tools, how are they responding with time. So, you can see here the hardness. So, the hardness property falls down drastically. So, you try to take, this is a carbon tool, steel. So, from the 80 HRC, it just falls down to 55 HRC by going to 800 degree Fahrenheit. So, when you take carbides from 95, it goes to somewhere around about 70. So, here is a response where in which we have drawn with respect to hardness and temperature. So, you can see that as and when the temperature goes high of the surrounding, there is a steep fall in the hardness property. For example, for a carbon tool steel from 80 HRC it goes down to 55 HRC by reaching a temperature of 800 degree Fahrenheit. When you take a carbide from 95, it goes up to somewhere close to 75 by at 1400 degree Celsius Fahrenheit. So, it is very clear, as and when the temperature goes high, the hardness property goes down. Hardness goes down, wear resistance goes down. So, this is very important. So, now you can understand there is a complexity while machining, and on top of it the tool geometry whatever is there also softens and changes, distorts. So, moment both these actions come into existence, we will never be able to get a proper cut. So, what people have done is people have thought of various ways. So, one way of doing it is in turning itself, rather than having a continuous contact of tool and the workpiece, what they said is, why don't we try to have vibratory assisted turning. So, vibratory assisted turning, vibratory assisted drilling is all used. So, what they do is they try to give a small vibration to the workpiece. So, the vibration can be along the z direction or can be along the xy plane. So, when you do that, they are trying to remove the complete contact of the polymer matrix composite with the tool and give a small elliptical motion, so that they try to reduce the damage and also tries to make sure that the heat gets distributed from the tool tip slightly. So, this is going to enhance the machining performance, and once it is enhanced, the amount of damage to the workpiece is reduced, because now the tool geometry is retained for a longer time. So, when you talk about a wear profile, you will always see this is the response of the wear profile. So, it is called as initial wear, then you will have a steady state wear, then you will have an accelerated wear. So, generally what happens when you try to use a HSS tool, we will try to resharpen at this place. Resharpening happens at this place. So, we always would like to work in the comfort zone of this. So, this initial wear happens in a very small time. So, basically what happens on the tool profile, there will be some asperities which are very thin and light. So, these asperities will try to die off very soon during the initial wear, and such that a large surface area comes in contact with the chip. So, this is a steady state wear and this is an accelerate wear. So, this resharpening is possible only for HSS tool. Why am I talking predominantly? If you have a complex geometry, we always use only HSS tool. If it is going to be a straight simple like a hole, a simple hole, a cylindrical part, a square box, a pocket if you want to make, so then we go for a simple geometry. If you want to do a slightly complex job, so then we always go for a HSS, because it gives you a freedom of grinding, regrinding, resharpening, so that you get to retain the old profile. So, when we do with respect to vibration, what happens is you can see the orientation in 0 direction and you can see orientation. So, this is the orientation with 0 degree, okay, and this is conventional cutting, this is vibratory assisted cutting. So, the vibration can also be low amplitude vibration, low amplitude high frequency, or it can be high amplitude low frequency. You can use any one of the vibration and try to get it. So, when you try to do without vibration, and that too in 0 orientation, I am talking about only 1-0 orientation, you can see there are lot of fiber pullouts coming out, and in vibration there is not visually seen fiber pullout. So, fiber pullout means the fiber is getting pulled out from its original position and then it is going to deteriorate the service condition of the part. So, here in vibration assistant it is not seen. So, when you see that at 90 degrees, you see there are lot of fibers which are getting pulled out, and there is this fiber which is getting pulled out are not also cut properly, but whereas when you see a vibratory assisted, there is a proper cutting and the fiber pull out is not there. See, if there is a fiber pull out after doing an operation, it is very difficult for you to trim the fiber and get the required output. So, if you see a typical setup of force measuring setup, so we will have this. If you look at a simple experimental setup for drilling alone, so we will have a spindle and the drill is mounted here. We will have a workpiece and we have a dynamometer. In this dynamometer, in drilling we will always measure a thrust force and a torque force. We will measure a torque force. Resistance to rotation is torque and the downward movement is a thrust. So, we always use to measure these two and then try to see what is the response while machining. So, if you look at a typical drill, you can see as and when the drill has not entered. If you see a drill, it is interesting. You will have a triangular portion and then you will have a cylindrical portion. So, this triangle portion is called as a conical area. This conical, before the conical area touches the workpiece, you see there is no change in the axial force. Axial force is a downward force. Moment it touches, you can see that the force increases from 0, it goes up to 300. The magnitude of the force depends on the resistance given by the workpiece. For example, thermoplastic will have a lower magnitude, metals will have a higher magnitude, thermosets will have in between these two. So, when it moment it touches, the load increases to P2, or from here touches, this is what it is, from P1 it goes to P2. So, you can see here this is the time. So, that means to say the drill is rotating and the drill is moving down. So, you have given a feed rate. So, it touches. So, moment it goes to P2, the conical portion comes in contact with the workpiece. You see here there is a force increase, and moment it is there, there is a fluctuation which is coming. This fluctuation is because of the presence of a fiber there, and the varying orientation of the fiber tries to dictate this fluctuation. Moment the tip comes in contact, the first thing what happens is it tries to extrude the material, extrude the polymer material into it. Okay. So, if you see here, moment the entire conical portion has entered into inside, till that time the force increases and it then comes down and it maintains. At P3, the conical is completely inside the workpiece. Now, after P3, the conical portion comes out. So, when the conical portion comes out, there is a fall in the thrust force. You can see there, as and when it is exiting, that the resistance goes down, the stiffness offered by the workpiece to the tool goes down. So, you can see the force declination, and then when it goes to 5, you see that completely the drill is out, you can see the thrust force coming up. So, with this you can try to see what happens to the thrust force at several instances, before entry, at the time of entry, during drilling, and then exit starts and exit ends. So, this is how the force profile looks like. Okay. So, this is another example which I have put. So, you can see the sharp increase is due to drill coming in contact with the workpiece. Okay. Then further increase due to cutting edge entering into the workpiece. The third portion is maximum force when the tool tip starts cutting the bottom ply. This will be the maximum force. After that, what happens? There is a declination, the sharp reduction then when the tool tip exits the bottom ply, and then you will have a gradual reduction with the decrease the contact length of the cutting edge will happen here, and then the drill gets exited out and then it goes out. So, these are the 6 steps which happens as and when the drill enters and goes out. This force diagram is very, very important. If you do not understand this force diagram, what happens during the process? So, here during the process here, there will be lot of delamination phenomena happening. See what happens here, there is lot amount of workpiece material which gives resistance to the tool cutting. As and when it goes to the last ply, the resistance goes down, the stiffness which is offered by the workpiece to the tool goes down. So, at this point, with the same force, what happens? It tries to eject out. So, when it ejects out, it is going to create a huge delamination. So, we are supposed to understand this and try to play with the forces such that the delamination does not happen. So, thrust force are always higher than the torque force. So, you can see the response of the torque force which keeps going on and on and on and then fall down. Why? Because the torque force keeps on increasing and then going further and further, because this is a rotation motion which is in the tool. When it rotates, it comes in contact with the hole. So, and then this force keeps increasing, and once it exits out also, So, if you go back and see here, even during the exit out, the exit there is a resistance, the tool is given a resistance by the workpiece. So, that the torque force will keep continuing at some level. The torque force is always lesser than the thrust force. So, in the initial stages of drilling, you will have a phenomena called as peel up phenomena. So, this the tip enters inside, and when this rotation happens, so this will try to indent and try to pull. Moment it tries to pull, it tries to do a peeling off operation at the entry. And when it comes to the last ply, that means to say bottom, almost close to the bottom exit, the stiffness offered is less. So, there is going to be a huge amount of fiber or we will call it as push down delamination at the exit. So, peel up delamination and push down delamination. Peel up delamination is not so prominent, because after this peel up also, since it is going to drill that surface, so this is getting compensated, but push down phenomena, the damage is going to be very high. So, this delamination to a large extent has to be controlled. So, you remember I told you several non-destructive techniques. We use those non-destructive techniques and try to quantify and see what is the amount of damage it has created. Then accordingly we try to choose the proper process parameters. If you look at it, the first hole, 30th hole and 50th hole, if you look at plain HSS, because of the tool geometry getting distorted, you see the fiber is not getting cut, but the fiber is pulled out of the matrix and it is left there. When you look at titanium coated, that means to say I wanted to enhance the temperature wear resistance. So, I do a coating on top of this HSS tool, and you see there is a slight enhancement, but it is not so. Okay. So, in the first one it is okay, second one. So, here if you see the damage, it looks slightly higher or it is almost maintained the same. So, here you should understand, when the TIN coating is given, the coating thickness plays a very important role. If it is done by a CVD route, the coating thickness is high. So, then there is a possibility of coating and the interface between the tool and the coating. This is the coating. If the thickness is high, then there is a delamination at the interface happening, and then this TIN peels off. So, sometimes coated HSS performs poor on a longer run as compared to that of the plain. So, if you look at tungsten carbide, the tool geometry is not damaged in a big way. So, the responses are good up to 50 holes. So, that is why when you see in aero industry, when they have a large wing where they do several holes, they just keep changing the drills after drilling 5 holes or 10 holes. They do not check all these things. They have established an experimental model. So, for every 5 holes or 6 holes, they keep changing the drill and then they keep going. When you look at the damage which is created because of drilling, so you can see that this is the diameter nominal I wanted, and this is the diameter which the maximum damage diameter. So, this can be expressed in a delamination factor, which is nothing but d max minus d norm by d norm. So, you will always have it in terms of ratio, and this ratio we will try to maintain it as low as possible. And if you see the delamination, it need not be uniform all across, it happens at several patches. The next one is the taper what we have. So, you can see that when we entry, this is the entry part and this is the exit part, and here on top of it you will also have the fibers which are projecting. So, this is a taper. So, these two qualities have to be maintained when you try to drill a polymer matrix composite. So, the several delamination measuring techniques we have seen in the non-destructive testing lecture series. So, we predominantly use microscopic and ultrasonic scanner to find out the defect, delamination and the response. So, now you see here there are various drill geometries which have come into existence. So, these drill geometries make sure that the thrust force is reduced to a large extent. If you reduce the thrust force, the push down delamination can be reduced in a large way. So, this is something like a tripod. So, we have 1, 2 and the center portion. So, the chisel, this is the chisel edge is now converted into a point, and these two edges are converted into other 2 points. So, here the thrust force reduces in a large way. So, this is called as braided point drill bit. So, in braided point drill bit, the geometry is changed and the thrust force is reduced. But this is a standard drill bit. So, this is a stepped drill bit. So, then you have a braid, then you have a straight flute which is there, or it is also called as dragger. Then we have multi-faceted drill bit. So, instead of 2 face, they are having multi-faceted. So, drill bits are available. You also have cylindrical drill bits, wherein which it is coated with diamond abrasives. This operation is called as trepanning operation. You have a core, a cylinder, and then a cylinder in the cutting portion is here top. We try to disperse it with diamond abrasive particles. So, here this because the chip is not continuous, you get a powdery chip. This geometry is also accepted for drilling of holes. So, this is a figure whatever I was talking to you about. So, people have also tried to, this is diamond abrasives coated on core drill. So, you can on a core drill. So, core, you can see a core twist drill, you can see a core saw drill, this is a core saw drill, then you can have a candlestick drill, then you have stepped cone drill. So, these are all different geometries today which people are using to reduce the delamination in a big way. So, as I was discussing in turning, people have also started using vibratory assisted, either the workpiece is vibrated or the tool is vibrated, again in ultrasonic frequency or a frequency which is lower than that. So, you can see the enhancement in performance of, see the thrust force, this is for vibratory assisted and this is for non-vibratory assisted. So, you can see the variation in the thrust force with respect to number of holes drilled for CD, UAD. These are a vibratory assisted drill and this is a conventional drill they have done, and you see the response whatever it is. So, this is CD with pilot, vibratory assisted with pilot. So, CD without pilot and UAD vibratory assisted without pilot. So, you can see the difference in response, how is it. So, milling of FRP composite which we are talking about, milling is generally used as a corrective end machining operation to produce, define or a very high quality surface. The fiber type reinforcement architecture and the matrix volume fraction are the most important factors which govern the tool selection and the machining parameter selection. So, what I am trying to say here is, if the volume fraction is 10%, if the volume fraction is 100 for the same or 80 for the same thermoplastic or thermoset, the process parameter and the tool geometry changes. If more the matrix, the chip to a large extent can be continuous. If more the particulates or more the reinforcement, it will be all powdery chip. So, in case of glass and carbon fiber reinforcement, it is the cutting tool material that dominates the tool selection. So, you look at it, thermoset and thermoplastic. Thermoset, the cut is clean because the matrix cannot expand or contract, it is already set, cured. So, you get a good cut of matrix and you see the fibers running along. So, in thermoplastic what happens, it is there is the matrix gets softened and it gets resolidified. So, you see there is a improper cut in the matrix. Okay. So, this is because of the recyclability property, or if you see at the microstructure, cross linking is 100 or very high here, cross linking is very less here. So, because of that, the after cutting is over, the polymer tries to distort and bring in a roughness. So, you see this figure clearly states there is a difference in the signature after cutting thermoset and a thermoplast. So, this leads to roughness. So, if you see here roughness variation between the two, you can see these are the values for milling. So, if you get optimized cutting edge, if you want, you can see this is the top view. You can see a milling cutter is cut, and then you can get a perfect channel made. If you try to use a blunt matrix material, so what happens is there is a distortion which is happening along the running direction, and the tool geometry is hit. So, some experiments results on surface quality when milling of FRP were performed as shown. The quality achieved when milling a thermoplastic matrix composite, you can see a perfect cut, optimized, and here you see a burnt matrix material because there is lot of heat which is getting generated. Moving to non-conventional, the most popular one is glass fiber is laser drilling composite. In laser drilling composite, laser beam, photon, lens, you would reduce the diameter. There is a laser, the laser jet comes and hits. If you want, you can also have a carrier media to gas to support, and then try to make a jacket and then use for cutting. So, the laser drilling can be done like this. You can do something called as a percussion drilling. You can also do a trepanning drilling. Trepanning drilling is you try to move around the round and generate a hole, and then you do it step by step by step. Say for example, if you want to do a hole, first you do up to here, then you do up to here. Okay. First, this is the first layer, this is the second layer, this is the third layer. You can keep doing it, and you move it in circles and get it done. The other way around is optical trepanning also can be done, and annular laser. You can change the profile of the laser, and annular portion can be thought of and it can be drilled. So, percussion, so what you do is you put a single pulse, you put more number of pulse, you burn layer by layer spot. You do not move the machine or the laser, you just keep it and then keep hitting at the surface, move the workpiece and get it done. So, both approaches are possible. If it is a larger area, we always use trepanning. If it is a smaller area, smaller diameter drill, we always do percussion drilling. So, here in laser, it is predominantly heat. So, it talks about the laser flux. Laser flux is nothing but joule per area. So, laser ablation is a process of removing material from a solid surface by irradiating it with a laser beam. At low laser flux, the material is heated by the absorbed laser energy and evaporated or sublimated. At higher laser flux, the material is typically converted to a plasma. Usually, the laser ablation refers to removing of the material with a pulse. See what happens when we try to remove polymer material while using a laser. This plasma is also getting formed. The laser the machining of laser has a big science behind it. So, there is recoil pressure which is coming into there is a plasma which comes into. So, all those things are beyond the scope of this lecture. So, all we have to know is this is what I talked about photolytic, and this is what I am talking about is the pyrolytic. Pyrolytic. So, pyrolytic means heat is applied for removal, photolytic means heat is applied, there is no heat, the laser has a wavelength, this wavelength interacts with the bond and it scissors the bond, the polymer gets sublimated. So, laser, the number of pulse, it can be femtosecond laser, it can be a picosecond laser, a nanosecond laser, it can be a microsecond laser. So, when it is a picosecond laser, the energy absorption, the adsorption by free electrons happens. When it goes to the picosecond laser, the electron lattice energy transfer happens. Then when it goes to nano, it is ablation by phase explosion or evaporation. When it goes to micro, it is going to be thermal diffusion, it is more going to be melt and resolidification. So, I have given you the mechanisms. So, this is the pulse interaction time with the workpiece. So, you will have, so what are the important things are wavelength of laser is very important, then you have time, lasing time, and then you also have repetition rate, which talks about in kilohertz, hertz. So, all these things play a very important role in deciding the mechanism of material removal from that. When you talk about laser, these are all the different process parameters which are involved in optimizing the heat affected zone and the taper to get a good hole or to get a good slot done. So, cutting velocity is important, environment is important, we can use assisted gas. Then focusing lens plays a very important. In focusing lens, focal length and focal positions are very important. Then when you talk about laser, it talks about whether it is continuous laser, pulsed laser, what is the source, beam divergence, what is the mode, whether it is pulsed. Then in pulsed, what are all the repetition rates and other things. So all these things are different process parameters which are used to see, which are to be seen before deciding the process and before making a choice of the laser. So here you can see type of fiber, it can be carbon, glass, armid, matrix can be epoxy, polyester, the texture can be unidirection, angular, woven or SMC, and the thickness also plays a very important role as far as material is concerned. Okay. So here if you see, people have started doing several modifications in the laser. Generally laser will have a waist profile. So this is a working zone where you can keep the workpiece and done, and then the laser beam expands or it expands. So in order to avoid this, what people do nowadays is they have start using a water jacket which is around the laser, such that the laser is always focused and it does not diverge. So you can get a very high aspect ratio holes made without taper. Okay. So this is how the modifications people look at it in order to get a proper lasing action on top of the workpiece. So you can see at the entry side, exit side, a cross section, you can always see a taper which is formed. So depending upon the choice of the laser, you can try to get good output. So here is a display which I have made for carbon fiber composites. People have started using water jet, and water jet also they have started using 5-axis machine, and it is basically a robo which is used. In the hand of a robo, they have given a water jet. This water jet nozzle tries to move over a surface to make 2D cuts. So you will have, when we talk about jet machining process, I said the either the water or the abrasives are increased the velocity by adding some carrier media to it. This carrier media pressure gets mixed with the abrasive or water, it gets pressurized and then it gets out through a nozzle, and then you do a machining. So you have an air compressor, then you have a dryer to remove the water content in the air, then you have a mixing chamber. If you want, you can bypass this, or you can have this abrasives. So the abrasive also gets mixed up with the air. So then this air is a carrier media, abrasive they get into the nozzle. So you use electromagnetic valve to open and close or to control, and this through the nozzle the abrasives come out with very high pressure, which on hitting the workpiece removes the material chip by chip or a piece by piece, and then you try to generate the profile whatever you want. So this is a water jet machining. So water jet is without the abrasives. Instead of this compressed air, I use water and then I pressurize water by a intensifier. So I get this. So this is a taper. Like in laser, you also get a taper depending upon the thickness. So here is the equation which is written for taper. So it is the arc tan W taper, the W top minus W bottom by 2T will give you the taper angle. So you can see that for from the front and back, which they have measured for a carbon fiber. So this is how it happens for abrasive water jet machining. So basically water comes in a very high pressure. There is a mixing chamber. So in this mixing chamber you can try to mix water and then abrasive, or you can try to have air and abrasive. Air and abrasive, it is called as abrasive machining process. Water and air is called as water abrasive machining process. So it comes out of the nozzle and then you try to do a machining. So when you try to do abrasive jet machining of polymer matrix composite, the most important setback of this process is you will have smooth zone and you will have a striated zone. This striated zone follows the profile of the jet, whatever it flows through the workpiece. So depending upon the thickness of the workpiece, this striated zone and the smooth zone proportion varies, and then you try to get a good cut. So this in turn we will try to optimize by choosing proper parameters. The proper parameters can be water pressure, or abrasive pressure jet, whatever it comes, then the feed rate at which the nozzle moves. So, these are the two important parameters on top of the abrasive size. So, when you see that, you can see divergence, you can see divergence, you can see convergence, you can see straight nozzles, straight channels are getting machined. So, you can, this depends on the traverse speed, that is the feed rate which I was talking to you. As and when you go higher and higher and higher, you see convergent happens when diverge. So, it's basically there is more time or less time for the abrasive to come hit at the workpiece and remove it. So, we always have convergent here, we will have divergent here, and if there is a taper, we always call it as a kerf width. So, this is what we are talking about: very rough surface, medium rough, fine and extra fine. So, these are the surfaces which are generated by using abrasive water jet while machining polymer matrix composite. So, in polymer matrix composite, there is not much of heat. So, the response of thermoset and thermoplast will be more or less equal. It will not be like in the case of heat. For example, when we use laser or when we use milling operation, there will be the thermoplastics expand and contract to give the output. So, the water jet can be used for milling. So, milling is basically what we are trying to talk about is to make pockets. Till now what we were seeing is only cutting. So, cutting means through to through cutting. Now, what we are trying to talk about is how do you mill a surface to get the required output. So, water jet milling. So, here the water jet cutting is used for machining of composite as well as sheet metals made out of steel and aluminum. The water jet cutting has a high velocity, water is forced through a small jet. So, then if you try to move the jet and make sure that it does a through cut. So, then it is more or less called as water jet milling. So, in water jet cutting, the process parameter that affect the cutting performance are going to be pressure, speed, laminate thickness and nozzle diameter. When it goes to water jet milling, the feed rate plays a very important role, and the feed rate plays a very important role. So, you do not allow a through cut to happen and get the required output. So, what I am trying to say is, suppose if this is the workpiece and this is your T. So, if you have a nozzle and through that nozzle if it is done, this is called as cutting. When you have the same thing, and this is your T, what have you done is you have the feed rates have increased and you do not give enough of time to make a through cut. So, these are called as water jet milling. So, the feed rate is one parameter which is very important, you do it. Okay. So, electric discharge machining of composites are possible wherever you want to do a metal matrix composite. So, there has to be a metal to finish the circuit. So, this is more predominant for metal matrix composite. Today people make copper based, people make magnesium based, people make iron based, people make aluminum based, then etc. These are the matrices which people are nowadays using in a big way, and the particulates, when I say metal matrix composite, the particulate is always the particulate composites are used. So, they are alumina, carbon, that means to say graphite, SiC or a combination is used, and then they make the workpiece. So, here since there is lot of heat which is between the electrode and the workpiece, there is a spark going to happen. So, there is a temperature phenomena. So, here it is heat is applied and then there is a subtraction process which happens here. So, here it is pretty interesting because in metal matrix composite you will have reinforcing agents also there. If the matrix melts, these are the particulates. So, if the matrix melts off, So then the particulates also drop. So here yeah, depending upon the volume fraction, you choose a proper process parameter and then you try to do. So since there are a lot of particulates coming up and then small bursts coming out, so the flushing becomes a very. So here, since the particulates are more, depending upon the volume fraction, if the volume fraction is very high, number of particulates are more. So if the particulates are more, matrix is less. If the matrix is less, the melting happens of the matrix. So particulate also falls down. So there will be lot of burrs which is there in the cutting zone. So these burrs have to be ejected out. So we always use a dielectric to flush these burrs out. And so when you say these dielectrics can flow from the side or through the tool to get the to remove these burrs and so from the cutting zone. So this is predominantly used for metal matrix composite, and of course if you can make a ceramic matrix composite conductive, so then that is also used for machining. So I have put down the properties which are there. So minimum required electrical conductivity of the EDM of a ceramic, if you want, it has to be 0.01 Siemens per centimeter square. So if you have that, then you can start doing the machining. So these are some of the electric discharge machine zirconium oxide based composites. So these are some of the things which are made out of it, and then people are using it. With this, we will come to an end of the machining lecture. So in this machining lecture, we predominantly focused on the polymer matrix composite, and then we saw different processes like conventional, non-conventional. How are these processes getting done, and how is it helps in doing the machining of composite materials. Thank you.